Hey guys, in this video we're going to talk about Chapter 15, Section 2, Optimization. So if you remember from Calc 1, optimization was where we had these real-world problems, right? We were trying to minimize cost or maximize surface area, minimize volume, something like that. And the way that we did that is we had a function in one variable. We found critical points of that function, and then we determined whether or not those critical points produced global maximums or minimums. Okay, and that's how we optimized functions in Calc 1. So we're going to do the same thing, okay, but it's going to be a little bit different because now we're in Calc 3, we're looking at multivariable functions. So the process is going to be almost parallel. It's going to be very similar, but there's going to be a few different steps that we have to take, and we have to kind of look at things in a new light. But I think this section is really cool. And so let's get going then and start talking about global maxes and mins. So I have these two definitions here from your textbook of global max and global min. And if you study these definitions long enough, it'll make sense. But basically, the global max is just the highest point on a curve, or in this case, a surface. So the highest point on a surface. And the global min is going to be the lowest point on a surface for some domain. Okay, so here I have just a generic surface, and notice they call it absolute maximum. Well, that's the same thing as global maximum. Okay, so absolute and global mean the same thing. It just means the bigger picture, if you think about it like that. The absolute minimum is also known as the global minimum, so I use global and absolute interchangeably. These mean the same thing. And then we have relative maximum, so the points around it, all of the points around it are lower than it, but it's not actually the highest point on the graph, like the absolute. So the relative maximum is also known as the local maximum, and the relative minimum is also known as the local minimum. So local and relative mean the same thing, global and absolute mean the same thing, just in case I go between phrases, you know what I'm talking about. But what we're going to do is, in this section, we're going to figure out global maxes and mins algebraically and graphically. And then we're going to talk about the extreme value theorem for multivariable functions. And it basically says that if our domain is closed and bounded, okay, this is similar to Calc 1 when we had a closed interval, the extreme value theorem tells us that there is going to be an absolute max or min on that domain if the domain is closed and bounded. So let's go ahead and proceed. Okay, so this is from your textbook again, the process of finding a global max or min for a function on a region D. Okay, they call it R in your book, but you'll see why I call it D in just a little bit. But it's called optimization. Okay, so just like we did in Calc 1, we're trying to find the absolute max or absolute min value on a function. This time our function is in multiple variables. So to locate global max or min, here are the steps. We want to first find the critical points. Okay, that's what we did in the last lecture. We looked at the critical points and we determined whether or not those critical points produced a local max, a local min, or a saddle point. Okay, we're going to investigate the critical points and see whether or not they give global maximums or minimums. And we're going to talk about this part in a few slides. If the region has a boundary, just like in Calc 1 when we had an interval. Do you remember the closed interval? We had something like x is bigger than or equal to 1, less than or equal to 2. We're going to investigate the quote-unquote endpoints, just like we did in Calc 1. Except this time, we don't have endpoints, we have, we basically have a disk, if you want to think about it like that, a flat, infinitely thin disk. And we're going to talk more about that in a bit. But Anyway, if the region does have a boundary, then we're going to investigate whether f attains a global max or min on that boundary, just like we did with a closed interval in Calc 1. Okay, so let's take a look at this surface, and we're going to figure out if it has a global max or a global min. Okay, so, or both. So the first thing I'm going to do is I am going to notice that I have a function. I have 3 variables, x, y, and z. So the first thing I want to do is I want to isolate z, just like you would isolate y in a function with only one independent variable. I'm going to isolate z because z depends on x and y. And to do that, I'm going to just keep my z minus 1 squared on the left side. And then I'm going to subtract over these guys to give me negative x squared minus y squared plus 49. From here, I'm going to take the square root of both sides. So I get z minus 1 is equal to plus or minus the square root of all of this. And then I'm going to add 1 to both sides to get z by itself. So I have a function of 2 variables, and I want to see what the max and the min is. Now notice I didn't specify a domain. So if there's no domain specified for x and y, you can assume x and y could be anything you want it to be. Alright, so later on we're going to talk about a specific boundary, which is basically the multivariable case of an interval. But for now, let's just assume that our domain is all real numbers for x and y. Okay. Alright, so now that we have this, we can figure out what the critical points are. And the way that we did that, remember what we did? We said, okay, well, we take the derivative with respect to x first. And so if I take the derivative of this guy with respect to x, I get, well, if I write this radical as a power of 1/2, I get 1/2 to the negative 1/2 times the derivative of the inside. Derivative of the inside is negative 2x. Remember, I'm just differentiating with respect to x. So again, I use the chain rule, and then I multiplied by the derivative of the inside, only considering x. All the y's and the other numbers are constants. So if I rewrite this, I get partial with respect to x is negative x, and then this is all over negative x squared minus y squared plus 49. Okay, just rewriting this, because negative 2x times 1 over 2 just goes to negative x. That's where I got that. And then I just put this thing back in the denominator. Alright, so this is where I'm at. And in a similar way, the partial with respect to y, you can verify this, is going to be negative y over the square root of negative x squared minus y squared plus 49. Okay? Now, if I set each of these equal to 0, I get x equals 0, y equals 0. And if I plug in x is 0, y is 0 into my original function here, I get z is equal to plus or minus the square root of 0 minus 0 plus 49. So the square root of 49 is 7, so I get plus or minus 7, and I actually forgot the plus 1 over here, so I can't forget that over there. Alright, so we have z is equal to plus or minus 7 plus 1, so I get z equals 8, and z equals negative 6. So what do these numbers tell me, right? I found the critical points, I plugged the critical points back into the function, and I got 2 points. I got the point x is 0, y is 0, z is negative 6. And I also got the point x is 0, y is 0, z is 8. So what do these points tell us? Well, what we could do is we could use the second derivative test to see whether or not these points produce local maxes or mins. And we can also verify, what these points are with a graph. Okay, so if I put this guy into GeoGebra, let's do that. Okay, so here is our graph. So we have a sphere, and the points of interest are labeled A and B. So A, we can see, is the very bottom point of the sphere. So that corresponds to the global minimum, and B is the absolute highest point on the sphere, corresponding to the global maximum. Okay, so let's investigate whether or not this function has a global max or min. So if you remember from quite a few videos ago, we talked about these things called paraboloids. And so a paraboloid with vertex at the origin had the form z equals x squared plus y squared. Okay, so notice that we have a paraboloid because we have x squared, y squared, and then a z, but notice that the x is shifted 5 units, y is shifted by pi, and we have a vertical shift up 2 pi units. Okay, so this is a paraboloid, and so we're going to expect that this thing has a global min. Now, if we find the critical points, we have to take the derivative with the partial with respect to x. So when I take the partial derivative of this guy, I get 2 times x minus 5, just using the chain rule right here. And then everything else goes to 0 because that's with respect to y and then a constant. If we take the partial with respect to y, in a similar way, we just get 2 times y minus pi. Okay, setting these equal to 0, I get x is equal to 5 and y is equal to pi. Okay, and finally, when I plug these back into my function to get z, I get z is equal to 2 pi. When I plug in y is pi and x is 5 pi, or 5. So I know that my only critical point here is 5 pi and 2 pi. And if we look at our graph on GeoGebra, we can indeed see that 5 pi, 2 pi is the absolute minimum of this graph. Okay, so it does not have an absolute maximum because notice that this thing just keeps getting taller and taller and taller. It grows without bound in the z direction, so there is no absolute / global maximum. Alright, does the function have a global max or min? Okay, so what we can do here is we can find the critical point, or critical points if there are more than one, and we get that by taking our partial derivatives and setting them equal to 0. So the partial derivative with respect to x is going to be 2xy squared. Partial with respect to y is 2yx squared. And then if we set these guys equal to 0, we get x is 0, y is 0. Okay. Plugging 0, 0 in here, I also get that z is 0. Okay. So, let's go ahead and look at this point when we plug our function into GeoGebra. Okay, notice that at the origin 0, 0, 0, we have a minimum, but also we have several global minimums, right? Because this thing expands forever out in the x and the y direction. So for any point on the x-axis or y-axis, we have a global minimum at 0. We can see that. Now, are we ever going to have a global maximum? Well, no, because this thing is going to grow without bound, right? You can see that with the graph. You can see it algebraically as well. We can make this as large as we want, right? Because our domain is, x and y can be anything. So we can make x squared, y squared as big as we want it to be by just making x and y really big. So we can make this as large as we want. However, we can't make this as small as we want. Think about why that's true. Why can't we make this arbitrarily small? Right? We can't ever have a product of two squares that gives us a negative number. That's the idea here. That's why this thing is bounded by 0, right? By the origin. Alright, so does the function f of xy equal negative 2x squared minus 7y squared have a global max or min? Well, right off the bat, if you think about it, since our domain is everything, all numbers for x and y, x can be anything, y can be anything, and see what z is, okay? It's not going to have a global minimum. No global minimum, so no absolute minimum, no smallest value for z, because we can make negative 2x squared minus 7y squared as small as we'd like. And to do that, we just take larger and larger values of x and y. That's the idea here. Because our domain, basically what our input can be anything we want, we can make our inputs huge, and that in turn, because of these negative signs, is going to give us an output that is really, really small, okay? So we can make our output as small as we want, therefore there is no global minimum, okay? But the opposite isn't true, right? Can we make this function as large as we want? So can we make this function as large as we want? Can we choose x and y values so that this thing goes to infinity? And the answer is no. Okay, so let's go ahead and figure out what our critical points are and then use those to analyze the graph. Okay, so if I take the partial with respect to x, I get negative 4x. If I take the partial with respect to y, I get negative 14y, just using the power rule. Setting these guys equal to 0, I get x is 0, y is 0. When I plug in 0 and 0 back into my original function, I get z is equal to 0. So my critical point is at 0, 0, 0. And we know that it's definitely not a global minimum, because we already said that just by looking at this graph, by choosing really big values of x and y on our domain, we can make this thing as small as we want to. Okay, so no global minimum is going to exist. What we could do is we could use the second derivative test to analyze this critical point. So that tells us that if we take the second derivative with respect to x, partial, we get negative 4. Second partial with respect to y is going to be negative 14. fxy is going to be 0. Okay, so for the second derivative test, we have d is equal to negative 4 times negative 14 minus 0 squared. This is positive, so d is a positive number. And this guy is negative. So when d is positive and our second with respect to x is negative, this means that we have a local maximum. Now, is this a global maximum? Well, let's take a look at our picture. Okay, so here is our picture here, 0, 0, 0. Indeed, that is going to be the global maximum because it is the highest point on the graph. Okay, so not only is it a local maximum, it's also a global maximum. Okay, so I want to find all the critical points and decide whether the function has global extrema on the xy plane. Okay, so here is my multivariable function. I've already taken the partial derivatives with respect to x and then with respect to y, so you guys should verify this, those of you watching. But we've done a million problems like these, so I just decided to give them to you there. Now what we want to do to find the critical points is we want to set each of these guys equal to 0 and solve. So we have 2y minus 3x squared minus 1 equals 0, and we have 2y plus 2x minus 1 equals 0. Okay, so notice that if I subtract these equations, the y's will cancel, which is really nice. So 2y minus 2y is 0. Negative 3x squared, we don't have another x squared term, so that's just negative 3x squared just comes down. And then negative 2x comes down as well. Negative 1 minus a negative 1 is a 0, and 0 minus 0 is 0. So we end up getting this when we subtract the two equations. Now, at this point, what I can do is I can factor out an x, and when I do that, I'm left with negative 3x minus 2 equals 0. And then setting each of these factors equal to 0, I get x equals 0, x equals negative 2 over 3. So plugging these back in for one of these equations for y, how about this equation, 2y plus 2x minus 1 equals 0. If I plug in 0 for x, I get 2y minus 1 equals 0, y equals a half. So 0, 1/2 is a critical point, and then when you plug in negative 2/3 into this function, you end up getting 7 over 6, which you guys should verify. So these are your critical points. So let's do the second derivative test. So the second derivative test, we need the second partial with respect to x second partial with respect to y, and then fxy. So partial with respect to x, that's just going to be negative 6x. When I take the second with respect to x, the second with respect to y is just going to be 2. And then when I take it with respect to x, and then I take it with respect to y, so I'm taking this guy with respect to y, that's just going to be 2 as well. Okay? So the second derivative test, we get this value d, right? So d was going to be negative 6x times 2. This is the second derivative test. We did a lot of these in the last video. Minus 2 squared. So we get d is equal to negative 12x minus 4. Now for this point right here, if I plug in 0 in for x, I get d is negative, right? 0 minus 4 is negative 4. And since that's the case, we know that this has to be a saddle point. This is by what we did last lecture. On the other hand, if I were to plug in negative 2/3 in for x, well, I would get d is equal to positive 24 over 3 is 8 minus 4, so this is positive. So d is positive, and what else do we need to verify? Well, we need to verify that d is positive and the second derivative is what? When we plug in negative 6 times negative 2/3, we get a positive. So since that's the case, since d is positive and also the second partial with respect to x is positive, we know that negative 2/3, 7/6 is a local minimum. And that was by, what we did in the last lecture. Now, so these were our critical points. Could there possibly be any global maxes or mins? Well, let's look at our original function and kind of determine from that. Let's see. So original function, we had f of xy is equal to y squared plus 2xy minus y minus x cubed minus x plus 2. And the question you want to ask yourself for if there's a global max, is there a global max? What you're asking yourself is, can we make the output of the function as large as we like? And if we can, then the answer is no, there is no global max. If we can make this arbitrarily huge, right, for some values of x and y, then there's no global max because this thing is going to go to infinity. It's unbounded. On the other hand, is there a global min? Is there a global min? You want to kind of ask yourself the opposite question. Can we make the output of this function as small as we'd like? So the answer to both of these questions are yes, okay? And because of that, there is no global max or global min. Let's take a closer look at this. So why is there no global min? So why no global min? Remember, x and y can be whatever they want. And, to see that there is no global min, to see that we can make this function arbitrarily small, what you can do is fix y. Say y is a number, how about 2? Right, we can do that, we can fix y. And if that's the case, then this function becomes 2 squared, which is 4, plus 4x, minus 2, minus x cubed, minus x plus 2. Okay, and then if we combine like terms and rearrange a little bit, we get negative x cubed plus 3x plus 4. Okay, so we fixed y, and now let's make x huge. So let's take the limit as x goes to infinity of this function. Now when x gets huge, this is a dominating power, right? It's the third power. So when this thing gets huge, this thing gets super, super small. So this goes to negative infinity. So we can make this function arbitrarily small, which means that there is no global minimum, right? And we did that by saying, okay, well, I'm going to show you there's no global minimum on this domain. We're going to say y is going to be just some number. We're going to fix it, say y is equal to 2. And we're going to show that when I plug in larger and larger values of x, when y is equal to 2, this function is going to go to negative infinity. Okay, so there's no global min. And we can do the same kind of trick with the global max. So for the global max, if instead we look at when the limit as x goes to negative infinity of negative x cubed plus 3x plus 4, well, then this is going to go to positive infinity, right? If this gets really, really small, right, this whole thing gets really small, well, negative times a negative is a positive. This is going to go to positive infinity. So no local, not local, I keep saying local when I mean global, no global max, okay? We can make the function as big as we want to by fixing y. We can make the function as small as we want to by fixing y, okay? That's the idea here. So no global max, no global min. But we do have a local min and we have a saddle point, and you guys should check this out on GeoGebra to actually see this in action. A closed rectangular box has volume 32 centimeters cubed. What are the lengths of the edges given the minimum surface area? So we want to minimize surface area, and we're given that the volume is going to be 32 centimeters cubed. So in a rectangular box, we have a length, width, and height associated with it. Those are the dimensions. And the volume is length times width times height. So we have this equation, length times width times height is equal to 32. And the surface area of a rectangular box is going to be 2 times length times width plus length times height plus width times height. Now, if this was a single variable calculus problem, we would be able to put our surface area formula in one variable. But we can't really do that here. We don't have enough information to do that. But what we can do is we can do the next best thing. We can put the surface area formula in terms of two variables. And to do that, I can use this equation up here to solve for one of my variables. I'll choose to solve for L. So I get L is equal to 32 over width times height. So I'll make that substitution everywhere I see an L here. So first thing, if I distribute the 2 in there, I get 2 length width plus 2 length height plus 2 width height. Now I'm going to do my substitution. So the surface area is 2 times 32 over width height times width plus 2 times 32 over width height times height plus 2 width height. Okay. So notice that W's here cancel, H's here cancel, and I'm left with surface area is equal to 64, H to the negative 1, right, just over H, plus 64 W to the negative 1 plus 2WH. And I'm trying to minimize this formula, or I'm trying to minimize this function rather. And so to do that, I need to take my partial derivatives, set them equal to 0 to find my critical numbers. Okay. So if I take the derivative with respect to h, okay, I get negative 64h to the negative 2. That, again, we're regarding w as a constant in this case since we're taking the partial with respect to h. And then this guy is going to be just plus 2w. Okay. Alright, if I take the partial with respect to w this time, I get negative 64 w to the negative 2 plus 2h. Now I want to set each of these guys equal to 0. So I get 0 is equal to negative 64 over h squared plus 2w. And then this one gives me 0 equals negative 64 over w squared plus 2h. Okay. So let's see, what should I do here? Well, what I can do is I can take this equation up here and I can multiply both sides by h squared, because I know that h isn't going to be 0. That would give us a very trivial case where length, width, and height are all 0. So if I do that, let me actually write the second equation over here. 0 equals negative 64 plus 2h. Okay. Alright, so if I multiply both sides by h squared, I get 0 equals negative 64 plus 2wh squared. And when I do some rearranging, I get w equals 32 over h squared. Okay. Now I can go back, take this, plug it into this other equation, and when I do that, I end up getting 0 equals negative 64 over 32 over h squared plus 2h. Okay. So let's see what I get when I do that. I get 0 equals negative 64 over 32 squared, which I'm not going to worry about what that is right now, but I know it's 32 times 32, over h to the 4th plus 2h. Rewriting this, I get 0 equals negative 64 h to the 4th over 32 squared plus 2h. And okay, so I get 0 equals, let's see, this is going to reduce to, let's see, negative 1 over 16, h to the 4th plus 2h. Alright, factoring out an h, I get h negative 1 over 16, h to the 3rd plus 2, and now I can set each of these factors equal 0. H equals 0 is the trivial case where our box, it doesn't exist, right? H, when we plug in 0 for h, you know, we don't have a height of a box, so that's not going to be our answer here, because we're talking about like a real world context here. But if I set the other factor equal to 0, I get negative 1 over 16 h cubed plus 2 equals 0. Negative 1 over 16 h cubed equals negative 2. H cubed equals, if I multiply both sides by negative 16, I get h cubed equals 32, and then I can raise both sides to the 1/3 power to get that h is equal to 32 to the 1 over 3. Okay. And I'm not gonna do this, but you should think to yourself why this is not gonna be a maximum value. Why is this not why is this the value that minimizes the surface area and not maximizes it? So that's h. The other dimensions, we can just plug h in right here to get w. It turns out when we do that, we get 32 over 32 to the 1/3 squared, and that's just going to reduce down to 32 to the 1/3 as well. And then finally, to get L, we can go way back up here to this guy, plug in L equals 32. Width we just found was 32 to the 1/3. Height we just found is 32 to the 1/3. And if we simplify all of this, we get length is also equal to 32 to the 1/3. So length, width, and height are all going to equal 32 raised to the 1/3 centimeters in order to minimize the surface area. Okay, so a few definitions here. A closed region is one which contains its boundary. Okay, so we've seen this before in Calc 1. You know, if I give you an interval, x is bigger than or equal to 1, less than or equal to 2, well, 1 and 2 are on the boundary of this set, right? Because they're at the endpoints. But this set includes 1 and 2, okay? So we call this set closed. All right, so that's closed if it contains the boundary. A bounded region is one which does not stretch to infinity at any direction. Now here comes our useful theorem, extreme value theorem for functions of two variables. If we have a continuous function on a closed bounded set, then that function attains a global max and a global min on the set, okay? So that's the idea here. If we have a closed and bounded set, instead of just the entire xy plane like we've been doing, if we restrict the domain to a closed and bounded set, then we're guaranteed to have a global max and a global min. So let's take a look at this example. So we want to find the global max and min of this function f of xy equals x squared minus 2xy plus 2 on a rectangle. So this is our closed and bounded region. Why is it closed and bounded? Well, if we take a look at what this actually looks like as a sketch, this is going to be a rectangle, right? So we have, you know, x is bigger than 0, less than 3, and then y is bigger than 0, less than 2. So we have 0, 0 right here, 0, 2, 3, 0, and 3, 2. Okay, so this is our closed and bounded region. And maybe I'll differentiate with colors. Let's have that be orange. This is green. Maybe we'll do this in blue. And how about this top part in red? Okay, so this is our closed and bounded region, our rectangle. This is D. And so what we need to do, just like in Calc 1, what did we do with Calc 1? Well, We were trying to find the absolute max or min. We found the critical points. We plugged those critical points into the function, got values for that. Okay? Then we compared those values to when we plug the endpoints into the function. We're going to do a very similar thing here, guys, but instead of plugging endpoints into the function, we're figuring out what the function is evaluated at its boundary. Okay, so these aren't just single points. This is entire line segments, as we can see in the 4 different colors. All right, so let's go ahead and first find the critical points, because those could be, possible contenders for absolute maxes and mins. So to find the critical points, I need to take the derivative with respect to x, and that's going to give me 2x minus 2y. Take the derivative, the partial derivative with respect to y, and that's going to give me negative 2x plus 2. Set these guys equal to 0, and I get x is equal to 1, y is equal to 1. So my critical point is going to be 1, 1. Now, if I plug in 1, 1 into this function, I'm going to get 1. Okay, so this right here could be a possible absolute max or min. Okay, now that I've taken care of this, I need to check the boundaries. Just like in Calc 1 when we check the endpoints, I got to check the boundaries. But first, these boundaries aren't just single numbers, they're line segments. So I need to describe these line segments, okay? So what about this first one, this orange one? Well, that's just a vertical line segment, x is equal to 0, right? What about the green? Well, the green is a horizontal line segment. That is going to be y is equal to 0, okay? And the red segment is going to be y is equal to 2. It's just a horizontal line. The blue segment is going to be x is equal to 3. So we need to check each of these. Okay, so when x is equal to 0, well, when I plug this into my function, it says, hey, x can be 0, but y can be anything, except y does have to be between 0 and 2. Okay, so we do have that restriction. Y is between 0 and 2. And when x is equal to 0, if we plug in 0 into this function here, we get 2y, right? We get 2y. So this is, maybe I should write it like this, f of 0y equals 2y. And the question is, what is the maximum and the minimum value on this interval here? Well, the minimum value is going to be when y equals 0, right? So 2 times 0 is 0. So this is a possible absolute max or min. The maximum value on this boundary is going to occur at the other end when y is equal to 2, right? When y is equal to 2, we get 2 times 2 is equal to 4. So that's a possible max. Maybe we should list this as an ordered pair. So this was when x was 0. When x was 0, y was 0, and z was 0. And this guy right here, when x was 0, y was 2, and z was 4. So this guy and this guy, these are possible contenders. These were on the boundary, max and min values. We also have this critical point that could be a possible contender. Now we have to look at the other 3 line segments and determine the max and min on those boundaries. So let's go ahead and do that. So we took care of the orange boundary. Let's look at the green. When y equals 0, we have x can be anything, x can vary, but actually x can only be between 0 and 3 because we're just looking at this green line segment. So we have f of x comma 0. Now if I plug in 0 for y into this function and leave x alone, I'm going to get x squared. Okay, so I'm going to get x squared. And remember, since we're just on this green line segment, x is going to vary between 0 and 3. Okay? And we can see on this interval, I mean, you can even graph this on Desmos if you want. We can see that the minimum value happens at 0 and the maximum value happens at 3. Okay, so the minimum value happens when x is 0, y is 0, z is 0, and let's see. Yeah, okay, sorry. And then the maximum value is going to be when x is 3, right, that at the other end. Y is 0, and if we plug in 3 for x into that guy, we get 9 for our output. So that is the max. So far we have 1, 2, 3, 4, 5 possible contenders for absolute max and min. Okay, now we have to check the red boundary and the blue boundary and we'll be done. So for the red boundary, we have y equals 2. And so again, f is going to vary, but x is going to vary between x is 0 and x is 3. So we have f of x comma 2. Now if I plug in 2 in for y into my original function, I get x squared minus 4x plus 4. And, just there's a few different ways that you can look at this, but anyway, this is a parabola. Okay, so there's our parabola, and we're varying between 0 and 3, so x is between 0 and 3. And the question is, where does this thing hit its max and min on 0 to 3? It might not be obvious at first, but, you can do a few different things. You can just plot this on Desmos and look. You can take the derivative and set it equal to 0, find the critical number, and figure out the max and min that way. That sounds like a lot of work. But yeah, I would just look at Desmos or recognize that this is the same thing as x minus 2 squared. So this thing is just, if you were to graph this, it's just a parabola shifted 2 units to the right. Right? And we're varying between 0 and 3. So where is this thing going to be minimal is going to be at 0, right, when this thing is 0. So in order for that thing to be 0, x has to be 2. So the minimum occurs when x is 2, y is 2, and if we plug in 2 in here, we get 0. So that's the minimum right there, okay? Now the maximum is going to occur when x is 0, right? We're going to have 0, 2, and if I plug in if I plug in 0 for x, I get 0 minus 2 squared. Negative 2 squared is 4. So that's going to be my maximum there. Okay, so these guys are also possible absolute maxes and mins. Okay, so far we have 2, 4, 6, 7 of them. And finally, our last boundary is the blue one. Okay, so this guy right here. So we have x equals 3 is our equation. We're varying from y equals 0 to y equals 2. Okay, so if I plug in 3 for x into my function up here, I get, let's see, I should get 9 minus 4y. And y is going to vary between 0 and 2. So this one is a little bit easier to see the max and the min. So the minimum value is going to occur here within this interval at 2. And the maximum is going to occur at 0. At y equals 0, I should say. Okay. All right. That was a lot of work. But now we have everything we need, and we just have to see which one has the highest z value. That's our max. So looking at all of our z values, we have z equals 1, z equals 0, z equals 4, z equals 0, z equals 9, 0, 9. Okay, so this one's the highest. So 3, 0, 9 is the absolute max. And now we look at the z values to find the smallest. So we have z is 0, z is 0. Yeah, so, and that's 0 as well. That just is a repeated point. So 0 is the smallest z value, so we have 2 absolute mins. We have 2, 2, 0 is an absolute min. And we have 0, 0, 0 is an absolute min, because both of those have a z value of 0. Alright, so we want to find the shortest distance from the point 1, 0, negative 2 to the plane x plus 2y plus z equals 4. Alright, so we want to minimize distance. That's what we're trying to do here. So let's start by just writing our distance formula. And we're trying to find the distance from a point on the plane. So x, y, z. Closest point on plane. Okay, so we want to find the distance between x, y, z and 1, 0, negative 2. And maybe I should just leave x, y, z as it is there. Alright, so let's go ahead and use our distance formula. We have x minus 1 squared plus y minus 0 squared plus z minus negative 2, so that becomes a plus 2 squared. Okay, so since we're trying to minimize this, we want to be able to take partial derivatives, and it's always easier to work in 2 variables if we can. 2 independent variables, rather. So what we can do is we can use this equation of the plane that was given to get z in terms of x and y. So if I isolate z in terms of x and y, I get z is equal to 4 minus x minus 2y. Okay. And I can just sub that in right here so that I'm in just two independent variables. So we have d is equal to the square root of x minus 1 squared plus y squared plus, instead of z, we have 4 minus x minus 2y plus 2 squared. Okay? And let's see, on the inside this becomes a positive 6, so I'm just going to replace that with plus 6. Okay. Okay, so we're trying to minimize this function right here. Now, minimizing this function is equivalent to minimizing the square of this function. So if we square both sides, just to make it simpler, we get d squared is equal to, when I square the square root, that goes away. So we get x minus 1 squared plus y squared plus 4 minus x minus 2y plus 6 squared. Okay. All right, so I'm going to go ahead and take the partial derivatives, because in order to minimize this, I need to find the critical points. So if I take the partial with respect to x, that's going to give me 2 times x minus 1 minus 2 times, well, I guess I can show you the steps. So this is going to be using the chain rule plus, and this shouldn't be 4, that 4 was gone. This is going to be 2 times negative x minus 2y plus 6 times the derivative of the inside, which is negative 1, right? Okay, so that becomes negative 2 on the outside. And that goes away. Okay. So if I simplify this, I get the partial with respect to x is 4x plus 4y minus 14. So that's that. In a similar way, I can figure out the partial with respect to y. And when I do that, I get 2y minus 4 times negative x minus 2y plus 6. And then simplifying this, I get the partial y derivative is 4x plus 10y minus 24. Alright, so now I need to set each of these guys equal to 0. Let me clean up this down here. Okay. Alright, so we have 4x plus 4y minus 14 equals 0, and we have 4x plus 10y minus 24 equals 0. So if I just subtract these equations, what I'm going to get is, let's see, 4y minus 10 is going to be negative 6y. Negative 14 plus 24 is going to be 10y, or just 10 rather, and then 0 minus 0 is 0. So solving for y, I get y equals 5 over 3. And then if I plug y back into one of these equations, either 1 or 2, I'm going to end up getting x is equal to 11 over 6. Okay? Now, I need to figure out the shortest distance. So I only found x and y that corresponds to the shortest distance. Now I have to go ahead and plug these x and y values into my distance formula. Right? So when you do that, when you plug 11 over 6 and 5 over 3 into just the regular distance formula, what you should get at the end of the day is 5 over 6 square root of 6. So this is going to be the shortest distance between the point that was given, 1, 0, negative 2, and the plane x plus 2y plus z equals 4.